No questions. All right. I put the next homework assignment on the web page. It's just one problem. I think it's problem 5.3, but I'm not sure. It's one about muon decay. All right. So, all right. So what we did last time was the famous LSZ reduction formula, and the one caveat was that we had moved the box operator through a time derivative and didn't worry about it. Today we're going to finish the calculation of the Feynman propagator and then look more carefully at what happens when you move a box across a time ordered product. And in fact, what we're going to do is we're going to be deriving the Schwinger-Dyson equations. And but first, let me go back to the Feynman propagator. Remember that a scalar field in Schwarz's normalization and metric and so forth, d cubed k 2 pi cubed, and I'm wondering what to call omega or e. I've got 2ek in my notes, so I better stay with that. Anyway, ek, of course, also known as omega k, is the square root of k of the momentum squared plus the mass squared. And then we have an ak e minus ikx plus ak dagger e to the ikx. And, all right, so let's compute what, and this is the 4-vector in a product. So let's compute in the vacuum of the free theory, and this, of course, is the free field dependence. I mean, the field has a free field dependence. The A is a constant in this expression. So we have phi of x1, phi of x2. What is this? Well, of course, it's just two of these. So it's d cubed x k1, d cubed k2, 2 pi to the 6th, the square roots of 2e1 and 2e2. And then the only way that you're not going to get 0 is if you take an A dagger from the second field and A from the first field. So I'm reviewing this. Is this too slow? Is this boring? Or maybe it's important. It's important enough that maybe it's worth doing a second time. And then we have minus I k1 x1 plus I k2 x2. Okay, but we know what that is because we know the commutation relations here are the commutator of A k1 with a dagger k2 is 2 pi cubed delta cubed of k1 minus k2. And so that cuts one of these down to 1 over 2 pi cubed. It sets k1 equal to k2, so the e's are the same. And what we've got then is d cubed k over 2 pi cubed 2e1 and e to the I k x2 minus x1. well, let's see, I've made a salad of the indices. So there's no subscript on K, so there's no subscript on E. This is, by the way, a Lorentz invariant expression. You've got a Lorentz inner product up here, and then you've got this dqk over E, which is the Lorentz invariant ratio. Now, we're going to compute not this, but the time-ordered product, or the mean value in the bare vacuum, some of this jargon, bare vacuum, vacuum of the free theory, same thing. And so we're going to be computing the time-ordered product of phi of x1, phi of x2 in the free theory, and that's just this times theta of T1 minus T2 plus 0 phi of x2 phi of x1 theta of T2 minus T1. So that's just what the time-ordered product is. And of course the theta function is this function that's named after Heaviside, who was a British mathematician, possibly Scotch, I don't know, these days we have to be careful. Anyway, I always think this is such an appropriate name because the function looks like that. And for negative time, it's 0. For positive time, it's unity. So it has one heavy side, and the other is a light side. And I don't know if, I guess he must have been amused by that. I always picture him as walking like this, but of course, never met the man. Any questions?
Are you sure about that?
Sure about what?
Is his name really Heaviside?
Oh, it is. But it's spelled with an I rather than a Y.
Oh, okay, so that makes it better.
And it's probably, you know, I can't pronounce it either in the English way or the Scotch way or the Welsh way, whatever he might have done. Okay, so this is our expression, and now if we use this formula for it, we see that this is in fact just an integral dqk over 2 pi cubed 2ek, well there's an ek here, I mean there's a k on the e. And so this is e to the ik, and if t1 is later than t2, then this is ik x2 minus x1 theta of t1 minus t2. So the thing is backwards because in the Schwartz metric you've got you've got the minus sign there, and that's what I'm here. And then the other one is plus e to the ik x1 minus x2 theta of t2 minus t1. Okay. So this is our expression, and of course the equality is going this way. Okay, it's the time-ordered product is this, and that is equal to this. Okay. Now we're going to let tau equal T1 minus T2. Sorry for the lopsided expression there. And we're also going to write this in three-dimensional notation here. And so this thing is going to be, by the way, I'm going to take advantage of a notation that Schwartz introduces a few pages forward in the book. the time-ordered product of something like that is just bracket phi 1, phi 2. So let me just write that there just to save board space. So it's this thing that we're calculating. And then in three-dimensional notation, it's d cubed k 2 pi cubed 2e k. And now what we've got is e to the I e t2 minus t1 minus I k dot. Now this is three-dimensional. x2 minus x1 theta of t1 minus t2 plus e to the I k ek t1 minus t2 minus I k dot x1 minus x2. Okay. And this is multiplied by the other heavy side function. And closing with the right bracket there. Okay. Now, well, we said we were going to introduce this tau being t1 minus t2. So let me do that with an eraser. This is tau. And this one here is minus tau. And we've got an e to the I k, e to the I e k. This is a tau here. And then we've got minus tau here. All right, so now we've got things more or less under control. Now what we're going to do here in this very first term, we're going to flip this 3 vector, and we can do that. We're going to let k, vector k go to vector minus k. That just doesn't have any effect on e, k, which occurs these two places, and it just means that we do the d cubed k integration in a different order. We do the 8th quadrant, and then the 7th quadrant, and then the 6th quadrant, rather than the 1st quadrant, the 2nd quadrant, 3rd quadrant. Okay, so now we've got a nicer expression, and it is integral across d cubed k 2 pi cubed 2ek, and now we've got e to the minus I k dot x1 minus x2. So this is the space thing, and what's left just involves energy and heaviside functions. And so that is left bracket e to the I, and we're going to do this one first. So it's e to the I ek tau theta of minus tau plus e to the minus I ek tau theta of tau. Okay, so this one goes here and that one goes there. All right. Now we're going to do a little bit of complex variable theory. Well, theory, goodness, I mean, it's just a concept. Standard there. And what we want to show is that e to the minus I ek tau theta of tau plus e to the I ek tau theta of minus tau, in fact, is equal to, and whenever we have epsilon, it's almost always in the limit epsilon going to 0, so I'm not going to write down limit epsilon equal to 0. I'm just going to write down what it is. Minus 2ek over 2 pi I integral minus infinity plus infinity e to the I omega tau d omega over omega squared minus ek squared plus I epsilon. So it was good that I decided to call that EK, otherwise we'd have two omegas, we'd be all confused. Okay, so we of course factorize this denominator, and it's minus 2 EK 2 pi I, of course, that means we're going to do a bloody contour integral. E to the I omega tor d omega, and now factorizing this, it is omega minus EK minus I epsilon, omega minus EK plus I epsilon. And now, let's work out, of course, the epsilon squared terms we ignore, because if epsilon 10 to the minus 10, epsilon squared is 10 to the minus 20, so forget about it. So let's multiply this out and see what the epsilon term is. Let me do it over here, because we always are short of blackboard space. If you multiply those out, what you get is I epsilon omega plus EK from one cross term plus EK minus omega for the other one, and that's 2I EK epsilon. So what's happened is that I epsilon has been replaced by 2EK I epsilon. But 2EK is just some some positive number, and so, in other words, I'm going to rewrite this. I mean, we can think of this as the same thing as I epsilon, okay, or as 2I epsilon if you want. All right. So we're all in the element epsilon going to 0, and that's the only epsilon in the expression here. All right, so now we've got this nice contour integral, and what we see is we've got two poles. We've got a pole just below the positive real axis and just above the negative real axis. So 0 is here, say. And okay. Now, what we can say is, yeah, I guess a step that I might have left out there. Let's write this as theta of tau plus theta of minus tau. Okay? And theta of tau plus theta of minus tau, whatever tau is, that's 1. Because this is just the two Heaviside functions. I just love the fact that he's named Heaviside. Let's see, are you getting this in? Now let's do the theta of tau term. Well, this only contributes when tau is positive. So we take tau as positive. If tau is positive and omega is up there near the north pole in the complex plane, up there in Fairbanks, okay, then you have two i's, a minus sign, exponentially suppressed. So what we do is we add this ghost contour like that, and we pick up this pole. And so what does that give us? It gives us minus 2EK, and the 2 pi I tells us, I mean, we now have in other words, what we have is now a contour integral, and it's omega minus EK minus I epsilon omega minus EK plus I epsilon. All right, so now we've got this integral. We're going around this pole, and so we get this thing here evaluated at omega equal to minus EK. And so this is equal to minus 2ek e to the I tau, but now omega is minus ek. And we also have this one. Omega is minus ek, so we get minus 2ek. And so, and of course this is times theta of tau. And so what does this give us? This gives us e to the minus I ek tau. Theta of tau. All right? On the other hand, this term tells us that tau is negative, and so we have to go down to Antarctica here to get suppression. So now we add a ghost contour this way. We pick up this pole with a minus sign because we're going around the racetrack the wrong way. And in fact, it's amusing, actually, the default for racetracks is also the default for contour integrals. I wonder if they're related. Maybe the first person to do this had been on a track team at some point. Anyway, what do we get for this? For this one, what we get is, well, minus 2ek, 2 pi I, integral e to the I omega tau. And now we're going around this pole, so we pick up this thing. So we have, well, let me just give you the answer rather than write everything down a second time. Well, we get minus 2ek, this coefficient. Then we get e to the I tau. Omega is now evaluated at ek. But there's an overall minus sign, so that becomes a plus. Omega, this is the pole, so we have omega is ek, so we have 2ek there. And so this is just e to the I ek tau, and again it's theta minus tau. So, what does this give us? This gives us e to the I ek tau theta minus tau, which is this term, and on the other hand, the first one gave us theta of tau e to the minus ek tau. Okay. So everything exactly as we want it, and that means then that we can replace the square brackets in this mean value in the free vacuum of the time-ordered product of two fields. We can replace it with this integral times what the square brackets are. And so that means that we've got 0 time-ordered product phi of x1, phi of x2 is integral d cubed k 2 pi cubed 2ek e to the minus I 3 vector k dot x1 minus x2. Then what's left is minus 2ek over 2 pi I integral d omega e to the I omega tau over omega squared minus ek squared plus I epsilon. So that's what we've got. And now there's an obvious cancellation. The EKs go away, the 2 pi becomes 2 pi to the 4th. And now we introduce a new variable. We're going to call it k0, but it's not the square root of k squared plus m squared. It's simply omega, which is an integration variable that we pull out of our noses and use to do the contour integration. So what we have then is integral d fourth k 2 pi to the 4th, and indeed it's also sitting there in Schwarz's metric, so it's e to the I k x1 minus x2, and in the denominator it's what? It's k0 squared minus, well, what's ek squared? That is k squared. In other words, we've set k0 equal to, which in Schwarz's metric is also k upper 0, equal to omega. And so this is k0 squared minus k vector squared minus m squared plus pi epsilon. And then there's the minus I, which comes up and becomes plus I. This is just k squared, Lorentz k squared. And so this is our Feynman propagator. d fourth k, 2 pi to the 4, e to the I k, x1 minus x2, I over k squared minus m squared plus I epsilon. That's the Feynman propagator. And what are we computing? We're computing the time order, the mean value in the bare vacuum or the free vacuum of 2 free fields, the time order product of 2 free fields. Computing the mean value in the free vacuum of the free theory of the time order product of 2 free fields. And that's the Feynman propagator. And that's the thing that, if you have a Feynman diagram like this wavy line or dotted line, that's this. It's representing this integral, where in a space-time diagram, that's x1 and that's x2. In a momentum space Feynman diagram, which looks exactly the same, now what this thing is, it's the Feynman propagator carrying this momentum k here. And you notice that k occurs as d fourth k and as k squared. And so if we interchange x1 and x2, it doesn't change anything. It just means we do the integration in a different order. All right, and this thing is called d sub f of x1, x2, and it's also equal to d sub f of x2, x1. All right, so that is the story about the Feynman propagator there. Any questions? Since we've been talking about Feynman, I heard there are many Feynman stories. One of them is that he was once at some conference, distinguished conference, and he was sitting next to Dirac. So he turned to Dirac and said, "Gee, what was it like to discover the Dirac equation and see that it got the right levels for hydrogen?" And Dirac's reply was, "It was a long time ago." Dirac didn't like to talk very much. Very sparing in his words. Any questions? Okay, let me just mention something about the Dirac what do you call it? Dirac propagator. If we have box sub x, say, sub x means we're differentiating with respect to variable x. Box plus m squared on the Feynman propagator x, let us say x and y. I could have said x1, x2. Anyway, so that is box plus m squared vacuum time order product 5x, 5y. what is it? Well, let me go over here. The box pulls down ik twice, so that's minus k squared. And then there's plus m squared, so it's minus k squared plus m squared. Well, in the denominator we have minus k squared, we have k squared minus m squared. We have minus what we get up top. And so this thing cancels apart from a minus sign. What's left is an integral d fourth k over 2 pi to the fourth, this space factor, that's delta function of, do you want me to do this in steps? Have I gone too fast? All right. Okay. So this is integral d fourth k, 2 pi to the fourth, I over k squared minus m squared plus I epsilon. The derivatives bring down minus k squared plus m squared e to the I k x minus y. All right, well this cancels apart from a minus sign. So this is minus I into the d fourth k, 2 pi to the fourth, e to the I k x minus y. And that, of course, is minus I delta fourth of x minus y. So basically, what is that telling us? That's telling us that the Feynman propagator is a Green's function of this differential operator. Apart from an I, normally with the Green's function, you don't have an I there. Yes?
So you just take the epsilon to 0 whenever it needs to be.
Yeah, notice that I said this is a Green's function of that differential operator. Good catch. Yeah, you were in the line of fire there, weren't you?
Okay.
All right. I said a Green's function, and that's because if we had defined this thing with a minus I epsilon, then that would have meant that we would have picked up, we would have done different contour integrals, added different ghost contours, we would have gotten a different set of Heaviside functions, and so we would have had a different boundary conditions or different, you know what I'm saying, I hope. All right, so, but this is the one that makes the most sense, the time order. All right. Now, we saw last time also that S matrix elements were, apart from what we'll be calling contact terms, they were written this way: e to the IP x box plus m squared over final states, product over initial states, e to the minus IPX box plus m squared. And then the vacuum of the full theory, time order product, the fields of the full theory. Okay, so that's what the S matrix looks like, again, apart from the contact term. Now, you know, the basic assumptions here are that fields, or at least boson fields, at different points in space, but at the same time commute, and on the other hand, that phi of x1 and t, the equal time commutator of that with conjugate momentum, is I, and if we put in the h bar, it's h bar delta cubed x1 minus x2, and of course, what is pi? Pi is the partial of the action density with respect to phi dot. And in most scalar field theories, that is just nothing more than phi dot itself. And so you can effectively say that this thing is actually phi dot. And in fact, Schwartz doesn't bother to put in pi at all. All right. Now, in a simple theory of a single scalar field, and that's what we're going to be thinking about today, the equation is Fox plus m squared phi of x equals, well, if the theory is free, 0. If it's not free, Lagrange's equations tell us that it's the partial derivative of the action density with respect to the field phi, and we've already got the mass term. In other words, the quadratic part of L is already included in this term, and so here what we have is the interaction Hamiltonian. So it's the part of the action density that doesn't involve the derivatives and doesn't involve the quadratic, that's not quadratic in, so in other words, let me just repeat what this is. This thing is normally like this. Derivative terms, phi dot squared minus half phi dot squared minus a half grad squared phi. The next term is minus a half m squared phi squared. And the next term is minus L interaction, or maybe it's plus L interaction. Yeah, it's plus L interaction, because what we're really doing is differentiating with respect to both of these. We get a minus, then we bring it over here. Okay, so that's what it looks like. What is Li typically? Well, the simplest possible case, which is actually very unphysical, but it's the one we're going to be talking about today because it's simple, is G phi cubed over 3 factorial. This is the simplest thing that's more complicated than just phi squared. The reason it's unphysical is that if phi assumes large negative values, the action density can go, well, if you write the Hamiltonian can go to large negative values when phi is negative. And actually there's a minus sign here, I think. God darn, got myself confused. Yeah, Li should have a minus sign if we're writing it this way. And a little. Yeah, okay, all right. So I think there's a recurring minus sign in Schwartz, actually. Maybe he fixed it. Anyway, let's go on with this and consider what happens in the case of an interacting field theory. In other words, we showed that for a free field, the box plus m squared on the time-ordered product of two free fields, that just gives us the Feynman propagator, and we worked out what that was. Now we're going to do the same thing but for the interacting theory. And what we'll expect to get is the following. So I'm going to show this, I'm going to derive this. box plus m squared on omega time ordered product phi of x prime, say, omega, that this is equal to omega time ordered product box plus m squared on phi of x times phi of x prime time ordered. So there's that, and then there's an extra term. And the extra term is minus I h bar delta of x minus x prime. And in fact, that's delta 4 of x minus x prime. So that's what I want to show now. And this is the contact term. So this is what happens when you bring a differential operator through a time ordered product. Well, obviously the only part of this that cares is the time derivatives. The spatial derivatives don't care about the time order, and the time ordering doesn't care about the spatial derivatives. Yes.
So this is box with respect to x.
Excuse me?
Box.
Oh yes, yes, absolutely. You guys are getting better and better at catching these things. We're going to tournament them later in the year. All right, well, let's look at the first time derivative. There's no problem with the first time derivative. All right, what is this? Well, of course, this is just d by dt omega theta of t minus t prime times phi of x prime plus theta of t prime minus t phi of x prime phi of x. And now what happens? Well, the derivative comes in here and it can act in 4 different ways. It can hit the theta, it can hit the t in the phi, it can hit this theta, and it can hit the t in this phi. And what do we get? Well, let me just use this board here. We've got a Heaviside function. This is like theta of t, say. If we take the derivative of theta of t, what do we get? We get 0 here, 0 there, but here, delta. So, ddt of theta of t minus t prime is delta of t minus t prime. Another way of saying that to make sure we've got the size right is that if you integrate the right-hand side, you get, going past, if you do a tiny integration of both sides around this point, you're going to get 1 from the right-hand side. And here, you're also going to get 1 because you go up by 1. So it's theta evaluated on this side minus theta on this side. And because one side is the heavy side minus the light side is 1. So that's the normalization. So what this gives you then is delta, derivative acting on that, minus delta because of the minus sign, and then derivative acting on that. So that gives you delta of t minus t prime times omega, and it's actually, you see, it's phi of x prime commutated, because you get, for phi of x prime, you have the delta function that comes from this one, whereas the delta function that comes from this one has a minus sign because of the minus t, and it has the x prime on the left. So that gives you a commutator. And then the other term is, the rest of it is vacuum time-ordered product of the derivative acting on phi of x prime. Okay. So in other words, if the derivatives just act on the field phi of x and not on the theta functions, then you've just got this same expression, but the derivative is sitting here, so it's the time-ordered product of the derivative, the time derivative of phi of x with phi of x prime. On the other hand, this term is 0. And so, as I said before, there's no problem in taking one time derivative through the time-ordered product. So that's what it looks like. Okay. But now when we try to take the second one through, we get a problem. All right, so let's do that. And we're out of space here.
So we have d by dt squared
All right. So now, what is that? Well, clearly that's nothing more than d by dt on the time-ordered product of dt phi of x prime, right? On the other hand, we learned what this thing does. Namely, this thing is going to be then, it can go through here, and we'll have time-ordered product of dt squared phi of x with phi of x prime. But then there's the extra term, and the extra term now is going to be the commutator of, in other words, it's going to be delta of t minus t prime, and then it's going to be the commutator of dt phi of x with phi of x prime. So in other words, in the first case over here, in other words, we could have done this, this could have been anything, this could have been A, okay? So the time derivative of the time-ordered product of A with phi of x prime is, well, it's delta of t minus t prime times the commutator of A with phi of x prime plus the time-ordered product of A with phi of x prime. And now we know what this is at equal times. It's just, this thing at equal times is just minus I h bar delta 4 of x minus x prime. Okay. So, what we have then is d by dt squared, time-ordered product, phi of x, phi x prime is time-ordered product of d by dt squared phi of x with phi of x prime. So in other words, if you want to be extra careful, you can do that. And then the extra term is this, and so delta times this is minus IH bar delta 4 times omega omega, but omega omega is 1. And so altogether this is just minus IH bar delta 4 of x minus x prime. And this is called a contact term. Okay, so we can now augment this delta t squared by subtracting grad squared, adding m squared, and so then what we get is box plus m squared, and let us say box of x plus m squared on, and now I'm using this notation of Schwartz where this means time ordered product. Okay, so these funny brackets mean time ordered product of whatever's inside. And mean value in the interacting vacuum, or if we're doing the free theory, the free vacuum of the time order product. And so this is the time ordered product of box plus m squared on phi of x with phi of x prime, and then minus IH bar delta 4, x minus x prime. Okay. So that's our, I guess that's the first, that's our first result. All right, so we're almost there. Well, I just said before that box plus m squared phi is equal to what Schwartz calls L prime sub I, and let me just look at this one more time to get these signs straight. All right. So we're writing the Hamiltonian this way, then this is the correct equation. The thing that bothered me a little bit is that the Li has to have a minus g over 3 factorial there. And so what we can do here is replace box plus m squared phi with L prime. And so this is equal to the time ordered product, mean value of the time ordered product in the vacuum, mean value in the vacuum of the time ordered product of the interaction density divided by the derivative of the action density with respect to the field phi. And this is evaluated then at x, and then phi 1. Well, in this case, it's just, yeah, let me just do this in 2 steps. So this is that times phi of x prime minus IH bar delta 4 of x minus x prime. Okay, so this is the simplest of the Schwinger-Dyson equations. But let's go back and look at this. What happens if you don't have one field here, but you have several? Well, then you have a more complicated time-ordered product. It's you have theta of, say, t minus t prime times theta of t prime minus t double prime times phi of x prime, phi of x double prime, and so forth. So now when the derivatives act, they act in more places. And the answer is box x on this time-ordered product of phi x, phi x1 dot 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 phi xn is time-ordered product box x phi of x phi x1 phi xn. So this is the case where you just say, oh, the hell with it, just move it through and don't worry about the theta functions. And then you get minus I h bar, a sum on j, delta, well, that's right. Delta 4 of x minus xj. And now, you see over here, we had two fields. The contact term has no fields in it. So now what we're going to have, instead of n plus 1 fields, we're going to have n minus 1 fields. And so it's going to be, for example, phi of x1 phi of x j minus 1 phi of x j plus 1 phi of xn. Okay. So those are the contact terms. And that's what we've got. And then if we just add the gradients and the m squared terms, what we get is the Schwinger-Dyson equation, namely box of x plus m squared on, and now we're going to use more compact notation, phi sub x, phi 1, phi n is L prime interaction at x, phi 1 phi n, and then minus I h bar sum on j delta 4 x minus xj, and now it's phi 1 phi j minus 1 phi j plus 1 phi n. Okay. So these are the Schwinger-Dyson equations. And again, this is for the case where when we're talking about a single scalar field and the Lagrangian looks a lot like that, or the action density looks like that. All right, well, these delta function terms are called contact interactions. And let me pause a moment, take a drink of tea, and maybe tell you another Feynman story. One of the things he liked us to do as a hobby was to grow roses and probably other plants. And this was when he was still in England, before he had come to the United States, which was, I guess, in the 50s or 60s. I don't know quite when, probably late 50s, early 60s. And some famous German physicist, Herr Dr. somebody or other, came to England to visit, to Cambridge to visit Dirac. And so this man, this German professor came by, and Dirac was down there on all fours, well, down there on his knees with probably one hand in the mud or in the soil and the other one pulling up a weed, and in the garden. And the German professor said, "Is Professor Dirac at home?" And Dirac said, "No," because he was in the garden, not at home. And my understanding is that the professor just left, and Dirac didn't bother anymore. Another story, just quickly, just because of the same sort, just so you don't get the wrong impression. Once he was giving a lecture, and of course he probably said, ask questions if you want. And one of the people in the audience, or maybe one of the students, raised his hand and said, Professor Dirac, I don't understand how you got from equation 3 to equation 4. And Dirac just went on with his lecture. And the student said, but I asked a question. And he said, no, you made a statement. Anyway, he was a very smart man. Everyone thinks about his sense of humor. Okay, now we're going to do, or at least start to do, the position space Feynman rules. And the equations we're going to get make a lot of sense. On the other hand, the pictures we draw in terms of them are a little bit mystical, but we'll do it anyway. All right. Now, the approach we're going to be taking here, and the whole business with Feynman rules, is what happens when you apply perturbation theory to quantum field theory. So, in other words, you assume the lowest order you have a free field theory, and then you do everything to first order and the coupling constant, then to second order, and so forth. All right, and we're going to use some abbreviations. Delta xi is going to be delta 4 of x minus xi. Dij is dji is going to be the Feynman propagator x1, xi, xj. We're going to obviously set h bar equal to 1 because these equations are going to get a little bit complicated. We're also going to set m equal to 0. Obviously, the mass term has not played a big role in this. It's m equal to the spectator. What is box x on d of x1? Well, we saw what that is. That's the second equation, or the first equation that's two lines under the clock over there. You see box, if you set m equals 0, then you get box on d is minus I delta. So this is minus I delta x1 in our new ultra-compact notation. The people who manufacture chalk are very much opposed to this notation. All right, so now we have phi1, phi2. This, of course, means mean value in the vacuum of the time-ordered product of phi of x1, phi of x2. All right, we're going to do something weird. We're going to write this as d4th x delta of x1 phi x phi 2. So that looks really stupid. Then we're going to write this as, well, delta x1, you see, delta x1 is I box x dx1. So we're going to write this as I integral d4th x box x dx1 phi x phi 2. All right. And now we're going to imagine we've got wave packets, so we can integrate by parts, drop the surface terms, and when we do that, and notice that this is a quadratic operator, so there aren't any minus signs when we integrate by parts. We integrate by parts twice. And so this is going to give us I integral d4th x dx1 box x on phi x phi 2. Now, on the free theory, if this were free, box x on this would be minus I delta of x minus y. And so, let me just write free. This would be then I integral d4th x dx1. Box on that is minus I delta xy. And now this just gives us the I times a minus I is 1, and this just gives us this just gives us d of y1. Somehow.
Where did y come from?
2.
Did I screw up?
It's not a y, it's a 2.
Yes, I think I did. Yeah, y should not be there, sorry. Thank you. All right, I owe you all a little bit of candy here. So the point is the box that is not 2, and now doing the x integration, the i's cancel, and we get delta 2,1, which is d21, which is also d12. And this, of course, is what we meant by that. Okay, so everything's consistent. Okay, who earned the candy? There were at least 2 people. Weren't there 2 people? You were one, right?
I cheated, I don't deserve candy.
Everybody else?
I'll take it.
All right. Okay, let me get on with the story, although this gets a little bit complicated. All right, so we're happy with this. This looks more or less sensible. All right. Now let's look at the time-ordered product of 4 fields. This is the 4-point function. So this is what we're really trying to do is the mean value in the interacting vacuum of the time-ordered product of 4 interacting fields, but we're doing it in the perturbative approach. Okay. So first we do this crazy maneuver here, where we set this, we say delta is I box D. So we write I d4 x dx1, and we've integrated by parts. So the box x comes along, and we have phi x, phi 2, phi 3, phi 4. Okay, so we first set delta of x1 equal to I box on that, and then integrated by parts, so the x came over. Okay, now what is this? Well, we go to the Schwinger-Dyson equation, which says box on phi x, bunch of phi's, is, and so I said interacting. For a while we're going to do the free theory, and then we're going to come back and do the interacting. In fact, from point of view of today, we're only going to do the free theory. So if we look at the Schwinger-Dyson equation in the free theory, L prime is 0, and this is just a bunch of delta functions with a minus I in it. And we have an I here, and so what that gives us is integral d4 x dx1, and then the Schwinger-Dyson expression for this is delta x2 phi 3 phi 4 plus delta x3 phi 2 phi 4 plus delta x4 phi 2 phi 3. All right, so that's the expression. How come there are plus signs and not a minus I? Well, we have an I here. All right. Now, on the other hand, each of these guys is just a Feynman propagator. And so this thing is integral d4 x dx1. And in fact, let me take advantage of the delta function to do the integration. After all, telling you all these Dirac stories, we can at least use the Dirac delta function. So integral d4 x delta x2 just means x gets replaced by 2. x by 3 here, x by 4 there. And so what this gives us, and then this one is d, this is the Feynman propagator, d34, this is d24, that's d23, and so this is d21, d34, plus d31, d24, plus d41, d23. All right. Now this again is, so far we're just doing it in the free period. Schwartz likes to rewrite this in pictures, and so we've got x1, x2, x3 down to x4, plus 1 to 3, 2, 4, plus 1, 4, 2, 3. All right. So he's writing these, in other words, each position, x1, x2, x3, x4, gets represented by a dot. Each Feynman propagator gets represented by a line. And that's the picture there. All right, any questions? All right, so now we're going to add the interactions, and I want to chase down this minus sign. It's nothing worse than the minus sign. So if this thing occurs this way, then well, I don't know why I'm saying that. Yeah, let's leave it a plus. I was wrong. Let's just leave it as a plus. And the reason, all right, here's the deal. Remember, I said this thing was unphysical. The physical case is phi to the fourth, as in the Higgs field. If you have a phi to the fourth, it has to come in with a minus sign because the Hamiltonian comes in with a plus sign, and they differ. And so in the case of the Hamiltonian, it has to be minus phi to the fourth. In this case, where it's simple but unphysical, it can come in with a plus phi cubed, and then you get a phi, here you get just g over 2 phi squared as the derivative. So L prime I is g over 2 phi squared. All right, I think we're basically, yeah, we're out of time. So this is a good time and place to stop, though, because what we're going to do next time then is this whole business but with interactions. And we may finish part 1 of the book on Wednesday. Any questions before we turn off the tape?